this video, we're going to look at the next topic in particle physics, and that is atomic or antimatter. So we want to learn what is antimatter and what is annihilation. So your task today is simply to watch this video and make some notes, and then I have one little question at the end for you, so you have no exam questions or anything like that. So first up, I'd like you to pause the video and just read this account. And this is an account from an unexplained event in an area called Tunguska, which is in Siberia in Russia. So just give it a read there, pause the video, give it a read, and then play the video when you're ready again. Okay, so once you've read that, I want you to have a look at this account. Now, these are two basically written accounts from some residents of the area of Tunguska. And basically back in, what was the year, 1908, there was this huge, massive explosion out in Tunguska, which is basically in the middle of nowhere in northern Siberia. And to this day, they haven't really fully explained what has happened there, but there's lots and lots of theories. One of the theories is that a comet landed, and a comet landed, this caused this huge explosion. Or another one, which is kind of a similar theory, is a meteorite. Some theories involve aliens. One is a volcanic eruption. One is a spacecraft explosion. And the last one is this thing called annihilation, which you wouldn't have heard of before. So scientists from all around the world, and there was a bit of secrecy kind of in this, around this whole event, went and they tried to investigate what actually happened, what caused this massive explosion in the middle of nowhere. And they searched the area, and there's a big massive crater there. You can look at YouTube and you'll find videos on this. And they found that there was no kind of material from outer space that wasn't of this world left there. And usually when there's a comet or a meteorite, or aliens I presume, you find some leftover kind of material that wouldn't be found in that area naturally, that it comes from outer space. And they couldn't find anything. So this was really, really unusual, and they kind of said, well, it can't be comets, meteorites, or aliens. They then had a look to see was there volcanic activity in the area, and again, they couldn't find anything. Alien spacecraft explosions, kind of the same, as they couldn't find any out of this world material. So one of the theories that's left over that hasn't been disproven yet is annihilation. Now, what is annihilation? Well, annihilation has got to do with antimatter, and we've met antimatter first, or already, but we're going to go into it in a little bit more detail today. And annihilation is something that happens when matter and antimatter meet, and you can guess by the word that it's fairly explosive, or that it's going to be a kind of massive release of energy. So when matter and antimatter meet, they basically destroy each other. And they release massive, massive amounts of energy. And that's one of the theories of what could have happened in Tunguska. But let's first talk about matter first. So, or antimatter. So all types of matter have what's known as an antiparticle. We've looked at protons, and it's doing that funny thing with the lines again. Protons exist across the Earth and across the universe. But there's also things called antiprotons. And antiprotons are exactly the same in terms of their mass. They're exactly the same size. The only thing that's different about them as far as you're concerned is, whereas protons have a positive charge, antiprotons have a negative charge. Same with electrons. We know electrons have a negative charge. An anti-electron is exactly the same mass, but it has a positive charge. Anti-electrons, by the way, are sometimes called positrons. There should be no end there, positron. So antiprotons and anti-electrons would make antihydrogen. So you could have, we know that a hydrogen atom is basically one proton and one electron. Well, an antihydrogen atom would be one antiproton, same size, just negative, and one anti-electron, a positron. Same size, same mass, just positive. It would have exactly the same properties of hydrogen. It would be a gas. The only thing is that it would have an opposite charge. Now, where did this antimatter theory come from? Well, basically, this guy, Paul Dirac, he won a Nobel Prize for kind of discovering or kind of coming up with the idea of antimatter. He was looking into the equations on the amount of energy that an electron has. And he got his solution, but in his solution there was a square root in his answer. Let's simplify it, square root of 4, which obviously it wasn't. But we know if there's a square root in your answer, there's actually 2 possible answers. The square root of 4 could be plus 2, or it could be minus 2. So when he got his answer, he was looking at his answer and he was saying, well, we know that there's a positive matter, but maybe there must be a negative matter as well. And he kind of came up with this idea that antimatter must exist. It's just that we don't really see it in the universe. And the assumption is that when the Big Bang happened, lots and lots of matter and antimatter were created, lots and lots of it. But immediately they met, and when they met, they annihilated and released all this energy. But they reckon that there was slightly more matter than antimatter. So pretty much all of the antimatter was destroyed, leaving just matter in the universe. And it's just that imbalance, and they don't know why that imbalance happened. Why is there more matter than antimatter, or why was there more matter than antimatter originally? But that's the theory that goes with it. Years later, a guy called Victor Heiss, and this is in your textbook, he actually observed antimatter coming from cosmic rays, and that's rays from the sun or from different stars. So antiparticles have exactly the same mass as the original particle, they just have opposite charge. Positrons are anti-electrons, and these are generated in nature, and these are the things that guy I mentioned, Victor, I'm going to limit the amount I'm writing here because it's making this funny line, Victor Heiss, he actually observed them in cosmic rays, which are rays from the sun. And there's something that we look at a little bit later on, and it's radioactive beta plus decay, and we've always done beta minus decay. So an electron, a positron, would have exactly the same mass as an electron, but its charge would be +1. So annihilation then. Annihilation is basically when matter and antimatter meet. So let's say, for example, I have a proton, and that proton collides with an antiproton. And what I'm going to do is I'm going to give this a P for proton, and the symbol for an antiproton is P with a dash across it. When they meet, when they collide, what happens is all of their mass is converted into energy. And we know our equation for mass being converted into energy is E equals mc squared. So if we wanted to figure out how much energy is created, we get the mass of this proton and this proton, they're both exactly the same. We put it into this equation and we get the energy. And then what happens is that energy is changed into photons. And we've come across photons before as well. And usually what you get is you get 2 photons. And there's reasons for this. And you remember before I was saying that certain things need to be conserved in any kind of equation or interaction. And the first thing that needs to be conserved is mass slash energy. So in this example, what we would have is we'd have 2 protons going in, or a proton and an antiproton, and they'd have kinetic energy. And whatever the total amount of mass slash energy is here, it must be the same as what you get out here. So you get 1 photon, and the symbol for a photon is gamma, plus another photon, plus they would have some kinetic energy as well. So that has to be conserved. The next thing that has to be conserved is charge. Now let's look and see, is the charge conserved? Well, we have a proton which has a charge of +1. An antiproton has a charge of -1. That's no energy. And then we have photons, and photons have no charge. So overall, the charge at the beginning is neutral, or 0. And overall, the charge here is neutral as well, because gamma or photons have no charge as well. So charge is also conserved. And the last thing that needs to be conserved is momentum. And this is one of the reasons why we have 2 photons formed, because this photon here is going upwards and it has a certain momentum. And in order for that momentum to be conserved, this photon has to be moving in the opposite direction. So the momentum before is equal to the momentum after. And really that's about all you need to know about the 3 of them. You need to be able to say mass energy is conserved. You need to be able to figure out, is charge conserved? And momentum is conserved because 2 photons are moving in opposite directions. So let's look at one example question. So we have a positron, which is an anti-electron, and electrons slowly meet. So here they're saying their kinetic energy is 0. So we have our electron plus our anti-electron, our positron, to meet. And they will form 2 photons. So they're going to have 2 gamma, gamma plus gamma. What is the average frequency of the 2 photons? Now let's look at this again. So we have our electron plus our other electron. So all of this mass is being converted into energy. So if we wanted to find out how much energy is being created, we'd use the E equals mc squared. Now the mass of an electron is on page 46 of your tables. And the mass of an electron is 9.1 times 10 to the power minus 31 multiplied by the speed of light squared. And in this case, there's 2 of them. So we could just multiply this by 2 because they both have the same mass. And we'll get an answer of 1.638 times 10 to the minus 13 joules. So all of that energy now is being turned into these photons. So we have these 2 photons. Now you might remember there was an equation that gives us the energy of a photon. And the energy of a photon, depends on its frequency. And it's equal to its Planck's constant multiplied by its frequency. So energy in equals energy out. So the 1.638 times 10 to the minus 13 is equal to the energy of the photons, but there's 2 of them. So it's equal to 2hf. And they asked for what is the average frequency of the photons. So what's their frequency? So the frequency would be 1.638 times 10 to the minus 13 divided by 2 times h. And h is Planck's constant, and that's on page 47 of your tables. And that is 6.626 times 10 to the minus 34. Type that into your calculator and you get an answer, and sorry it's squashed, you get an answer about 1.24 times 10 to the 20 hertz. And that's your answer. Sorry about these lines, but I don't know how to stop it. Why are the 2 photons moving in opposite directions? Well, your answer is to conserve momentum. That's all you have to write, conserve momentum. Okay, so hopefully that makes a bit of sense. Just make some notes on this and I'll give you the page numbers from your textbook as well. And then what I'd like you to do is just try this one question. This question is similar to the ones that we've just done, but there's also some kinetic energy involved, and that kinetic energy is given to you in electron volts, not joules. So remember, the first thing you need to do is convert this to joules. So try this question, and first thing tomorrow is I'll go through this question with you, and then we move on to the next topic.